Welcome to the Learning Curve. In this lesson, I will be continuing my special series on reviewing content, typical final exam questions for university students studying Calculus 1. In this particular question, we'll be evaluating homogeneity and Euler's theorem. This question says, find the degree of homogeneity of this implicit function. This is an implicit function because it is expressed in terms of more than one variables, in this case x and y. So we're asked to find the degree of homogeneity of f of xy equals x cubed plus 2xy squared plus 2x squared y, and show that the function satisfies Euler's theorem. In order to find the degree of homogeneity of this function, we're going to substitute kx for x, where k is a constant coefficient, kx for x, and ky for y. So I'm going to rewrite this as f of kx, ky, and this is going to be equal to kx all cube. Wherever x is in this implicit function, I'm going to replace it with kx, and wherever y is, I'm going to replace it with ky. You're going to see why this approach is taken soon. So kx all cube plus 2, and where I see x here, I'm going to replace it with kx, and where I see y, I'm going to replace it with ky. So this will be ky all squared plus 2 multiplied by, and here where we have x, I'm going to replace it with kx all squared, and where I have y here, I'm going to replace it with ky. Now we're going to try and simplify this. So this is going to be k cube x cube, yes. Kx all cube can be expressed as k cube x cube plus 2 multiplied by kx is going to give us 2kx, and ky all squared can be expressed as k squared y squared plus, here, before we can multiply this bracketed term by k, we will first have to evaluate the bracket by raising it to the power of 2. So here I will get 2. When we raise kx all squared, we'll get k squared x squared, and I'm going to write back the ky that is out there in the bracket. Now let's see if we can simplify this a little further, and it appears that we can. So I'm going to write back k cube x cube here plus, now we're going to multiply any term that is common here. K to the first power and k squared can be multiplied by each other. So this entire expression here can be written as 2k cube, and then I write back the other terms in the product, which are xy squared. So I multiply this k to the first power by this k squared here, which gives us k cube because we add the powers. Invisible 1 here, plus 2 gives us k cube. Plus, here we also have a k squared and a k to the first power here. So we can multiply them by each other. K squared multiplied by k to the first power is going to give us k cube. And then I write back the other variables that make up this product, which are x squared and y. So now we're going to look at this function. We're going to look at all the terms in it. And we're going to see if there's any term in k that is common. And this was the whole point of seeking to substitute for kx and ky, rather to substitute kx and ky respectively for x and y in the implicit function, because we wanted to identify a value in k, an expression in k that we could factor out at the end that is common to all the expressions that make up the rewritten implicit function. When we look at this, we realize that here we have k cube, here we also have k cube, and here in the third piece we also have k cube. So we can factor out k cube. So when we factor out k cube, because it is common to all three expressions making up this sum, here, here, and here, when we factor out k cube goes into k cube x cube times, because k cube would cancel itself. And then k cube divided into 2k cube xy squared would give us 2xy squared, because again the k cube would cancel. And when we divide k cube into 2k cube x squared y, again the k cube would cancel, so we'll be left with 2x squared y. It's important to notice here that essentially we end up back with the original function when we factor out k cube. So x cubed plus 2xy squared plus 2x squared y is exactly the same as the original function here that we're given, which is f of xy. So I could simply write this as k cube bracket f of xy. K cube f of xy, because f of xy is exactly what is represented in the bracket here. So we could write it as k cube f of xy, and then we identify the degree of homogeneity. Homogeneity, of course, indicates sameness, and the common expression in k, which is found throughout this entire implicit function, is k cube. So the power of k here that we factored out is 3. And so whatever the power of k is that is factored out after taking this approach of substituting kx and ky for x and y respectively, that gives us the degree. So the degree of this implicit function is 3. That is this 3 right here, which is the power of k that was factored out from this implicit function. Now, the next thing that we're going to do here is that we're going to identify whether this function satisfies Euler's theorem. So we're going to show that the function satisfies Euler's theorem. That's what we're asked to do. So to show that the function satisfies Euler's theorem here, we're going to need to carry out some differentiation. So we're going to multiply x by the derivative of the function with respect to x plus y multiplied by the derivative of the function, that is the implicit function that we were given, the original implicit function here, the implicit derivative. So the d here, d that we're using here indicates that we are differentiating implicitly. And differentiating implicitly, as you will see soon, means that when you're differentiating in terms of or with respect to one variable, the other variable is treated as a constant. I will discuss that further. So here, we're going to multiply x by the derivative of the function with respect to x plus y by the derivative of the function with respect to y. This is because there are only two variables in this problem, x and y. If there were other variables, such as, for example, if there was z, we would also add plus z times the derivative, the implicit derivative of the function with respect to y, with respect to z, rather. Okay? So we're going to carry out implicit derivatives here. We're going to differentiate implicitly. So let's see how this works out. So it's going to be x multiplied by, let us keep the original implicit function that we're given here in mind. So we're going to differentiate the function f, this function here, with respect to x first of all, which is what we need right here. So differentiating this implicit function with respect to x is going to give us 3x squared, yes. When we differentiate x cubed, we get 3x squared. Of course, the 3 comes down to the front and we take 1 from the power. So we get 3x squared. Now, when we're differentiating 2xy squared, essentially what will happen here is that we are going to treat the y as if it is a constant. Okay, we're going to treat we're differentiating with respect to x. So both the 2 and the y squared that are multiplied by the x will be treated as constant coefficients of x. So we're going to treat 2y squared as a constant coefficient of x because we're differentiating implicitly. So that this would therefore become plus 2y squared. Again, we're treating 2y squared, which are the terms multiplied by x here, as a constant coefficient of x. As I indicated previously, when you're differentiating implicitly with respect to a particular variable, the other variable or variables are treated as constants. And that is illustrated here to get the 2y squared. Now I'm going to have plus. Now when we differentiate 2xy squared here, so we're focusing on 2x squared y rather, focusing on 2x squared y here. When we differentiate 2x squared y, we're going to be treating this y as if it's a constant, as if it's a number. When we differentiate 2x squared itself, we get 4x, and we write back the y because we're treating it as a constant. So 2 multiplied by 2 gives us 4 here. We take 1 from the power, so we get 4x. And since y is being treated as a constant, it will remain as part of the differentiated result. So here we have worked out the derivative of the function implicitly with respect to x. Now we're going to say plus y multiplied by, and what we're going to do now, because this is what Euler's theorem states, is that if we are able to differentiate this function, x multiplied by the derivative of the function with respect to x, plus y multiplied by the derivative of the function with respect to y. If this implicit function satisfies Euler's theorem, then what will happen is that when we simplify this, we will get the degree of the implicit function multiplied by the original function here itself. So if we can get the degree, which is 3, multiplied by this original function, f of xy, then Euler's theorem would have been satisfied. So let us now multiply y by the derivative of the function with respect to y. So when we're differentiating the function with respect to y, we're going to treat x, which is the other variable in the function, as if it is a constant. So differentiating this function here with respect to y, there is no y in the first expression, x cubed. So treating x cubed as a constant, when you differentiate a constant, standing on its own, you get 0. Now let's differentiate 2xy squared. When we differentiate 2xy squared here, the 2 will come down to the front and multiply by 2. So we're going to get 4. And because we're treating x as a constant, it will remain part of the product result. So we get 4xy. Plus, now, in the derivative of 2x squared y, we're treating 2x squared as if it's a constant coefficient of y. So the derivative of 2x squared y with respect to y would just be the constant coefficient of y, which is 2x squared. All right, so that is the result that we have there so far. And then we're going to attempt to simplify this by multiplying by the term in front of the bracket. Doing that, when I distribute x throughout the entire bracket here, we will get 3x cubed plus 6x multiplied by 2 here is going to give us right, so x multiplied by 3x squared is going to give us 3x cubed, and x multiplied by 2y squared is going to give us 2xy squared, and x multiplied by 4xy is going to give us 4x squared y. Then we're going to go over this side and say plus, well, y multiplied by 0 is going to be 0, so we can leave that out and just say y multiplied by 4xy is going to give us 4xy squared, and y multiplied by 2x squared is going to give us 2x squared y. Now we're going to try to see if we can group like terms. So are there any common terms here which we can pull together? And the answer is yes. So we're going to have 3x cubed. Now let us see what else we have in common. We also have plus 2x y squared. And this term is also a term where the power of x is 1 and the power of y is 2. So we can add those two. So plus 4x y squared. All right, so we can add these two together because the powers of x and y are the same. Plus 4x squared y right here. And we realize that the power of x and the power of y here are the same right here. So it's going to be plus 2x squared y. Now we can add these two terms because the y and the x's have the same power. So let us now simplify. 3x cubed. When I add 2x y squared plus another 4xy squared, we'll get a total of 6xy squares. Then when I add 4x squared y plus 2x squared y, it will also give us 6x squared y. Now these two terms here, 6xy squared and 6x squared y, cannot be added because the powers of x and y are different. So now that we've reduced this expression, this whole expression to the derivative expression to its simplest form, we now ask ourselves the question, what is the highest term that I can factor out? What can we factor out here? Well, we can easily factor out 3. 3 is common to all of these, right? In fact, 3x is common to all of them as the highest common factor, but we can factor out 3, which is the degree. So once you have brought it to its simplest form, you ask yourself, am I able to factor out the degree that was established for the implicit function or found for the implicit function? Can I factor out the degree? Yes. Easiest way to do it, once you have reduced the derivative to its lowest form, is to see if you can actually factor out the degree from the result that was found. So yes, we can factor out the degree here. When I factor out 3 out of 3x squared, 3 divides into 3x cubed rather, 3 divides into 3x cubed, x cubed times. I can also factor out 3 out of 6xy squared. 3 will go into 6 2 times, so that is going to give you 2xy squared. And 3 can go into 6x squared y 2 times as well. So that will give us 2x squared y. Now I want you to look at what we have in bracket here in the result and look at the original polynomial, the original implicit function that we had. Here, x cubed plus 2xy squared plus 2x squared y. What do you notice? You notice that it is exactly what we got in bracket here. So what we notice, therefore, I'm going to say here that x multiplied by the implicit derivative of the function with respect to x plus y multiplied by the implicit derivative of the function with respect to y gave us n multiplied by, where n represents the degree of the implicit function, it gave us n multiplied by f, n multiplied by f of xy. Once this condition is satisfied, which it is in this case, Euler's theorem is satisfied. That is, when we found the derivative, we got 3f of xy, which which is what this really is, 3f of xy. Because as I indicated earlier, all of what is in the bracket here is f of xy. So the answer works out to be 3f of xy. Once the derivative works out to be n, where n represents the degree of the implicit function, multiplied by f of xy, once you can simplify it to that form, then Euler's theorem has been satisfied. All right? So we conclude, therefore, that this proves that the implicit function, satisfies Euler's theorem. Satisfies Euler's theorem. And I will be doing many more questions from the calculus syllabus on Euler's theorem to prove that particular implicit functions satisfies Euler's theorem. I hope you found this to be a very clear and easy to follow lesson. And remember to keep posted to the channel for much more material on calculus, mathematics at various levels, and like, share, and subscribe as we continue to indulge in the world of mathematics. Thank you. See you soon.